So continuing on yesterday's session, it's the first time that we introduced the concept of competing hypotheses. Now, your null hypotheses, that's your sort of your conservative standpoint. And we took the frequently used innocent until guilty example, at least is the one we came up with yesterday. H naught is what you could imagine as the status quo, as you don't, it's the thing that's not going to get you too excited. And in the case of what we're doing in this chapter, we're plotting for the purposes of investigating whether there is a relationship to variables. We're plotting our x variable and our y variable in a more general setting. Your input variable would be made up of multiple variables, the ones that we usually enumerate from 1 to p, made up of several factors. That's your observation, and you're trying to predict. This is a chapter on regression, specifically linear regression. You're trying to predict quantitative output. It's different to a classification model where, well, that's classifying. And the example that we've often discussed here is someone defaults or they don't default, or political party A, political party B, or an insurance claim is settled in court or out of court. In regression, we're not classifying. We don't have these binary or finitely many outputs, which is what you'd have in a classification problem. And very often they wouldn't be numerical, but like we said, political party A, political party B. But we're trying to predict a numerical output labeled Y. And in simple linear regression, so taking the problem down a further notch in terms of complexity, in simple linear regression, it is simply the case of plotting one numerical variable, x, that is your input variable, that is your predictor variable, against y. Now, without looking at anything else, let's see how much we remember, and that includes me over here. These two charts are doing basically the same thing, but the right-hand side, and if we find my cursor, we can just emphasize it in pink, just in case we get our left and right muddled up. The right-hand side is doing what the left-hand side did, but 10 times. So it has tried to approximate the red relationship, which is the true relationship, which is the relationship we won't have in practice, for the simple reason that if you knew the true relationship, then why create a model in the first place? But 10 times, and 10 times in what sense 10 times? Based each time based on a different data set. And what we said yesterday was, imagine each one of us going out, collecting our sample data, which is going to be a subset of the overall population that we're trying to understand. And there will be different biases in each one of our data sets. So my data set might be biased one way. The biases might be minor. They might be statistically insignificant. but you do expect some level of bias in your data, which is why when each one of us would then perform linear regression on our data, and these diagrams, we're seeing it in detail for one specific data set. I'm going to use orange. We will each get a different line, a different blue line. And remember, the blue line is uniquely defined by two parameters, your beta naught and your slope, beta 1. Now, there's the true beta naught and the true beta 1. Those are the y-intercept of the red line and the red line's gradient. That's the true relationship. Instead, what we do is we estimate those betas. So whenever we write our estimated beta naught and beta 1, we write, or we include a hat above each one. How is this performed? Well, in linear regression, the most commonly used approach is least squares method, where we minimize the residual sum of squares. What is a residual? The residual is simply the difference between your model's prediction and the actual observation. So this is always a function of your data set, of the data that you used to create the model. So when we speak of a residual sum of squares, this is very similar to not the test mean square error, but the training mean square error. We need beta naught hat and beta 1 hat to solve two equations. Which two equations? Those two equations that come about using calculus to minimize not the curves that we study at A level, but this is a multi-dimensional problem. It's the easiest one. From all the multi-dimensional problems, it's the one where we have two dimensions. So we're studying a surface. We're studying a surface. We look at all the possible beta naught values and beta 1 values. Each combination, each pair of beta naught and beta 1 gives you one value for the residual sum of squares. We minimize that residual sum of squares using differentiation. It's very, very similar to what we do when we locate turning points on curves, with the difference that it's multidimensional. So instead of using exact derivatives, I'm referring to d by dx, we will use, the book doesn't do it, at least it hasn't done it at this point. We use instead partial derivatives. So we differentiate this function. This is a function of two variables. So you can think of it as RSS of beta naught and beta 1. We find beta naught hat and beta 1 hat that minimize this function. That's linear regression. That is simple linear regression. We need to estimate two parameters, an intercept term, that's beta naught, and a slope term, that's beta 1. Only thing is that it's contingent on the data that we're using. And this is what the book is emphasizing over here. If we collect 10 different data sets capturing the same kind of information. Yesterday, we were talking about the heights of individuals in a specific country. You're not going to ask each single individual their height. It's usually not feasible. And even if you did so, there would still be errors in just maybe measurements, and maybe when people quote their height, maybe they perhaps add an inch or two just to make themselves sound taller, or they subtract to make themselves sound shorter, or whatever the case, right? One of those, the grass is always greener on the other side. Each data set gives you a different model. Your model depends on the data that you collect. So if you were to do it 10 times, and we keep on repeating the same ideas, the same steps, but they are worth repeating, in my opinion. Definitely good return on investment. We get all these different lines. So we cannot, there's no way that we would ever feel that our estimated beta naught and our estimated beta 1 are the true beta naught and beta 1. And we spent quite a good chunk of yesterday's lesson discussing the error within the estimate of each parameter. We have two parameters since it's a simple linear regression. Simple means you're only taking one predictor variable. You're looking at individuals' heights based on their mother's height. One single variable. It definitely gives you quite a bit of information. And let's make it clear. You can always include more variables to get a model that's closer to reality. Now, how do we measure error in the case of estimating these parameters? Again, the hat emphasizes this is an estimate. We haven't used the entire data set. The data isn't necessarily a linear relationship in any case, but assuming it is a linear relationship, how good is my estimate? And this is where our last session spent quite a bit of time constructing these confidence intervals. And it's quite standard to speak of 95% confidence, although if you're ever working for an insurance company that operates within the European Union, they have certain capital requirements that operate not on a 95% confidence interval, but on a 99.5%. And that's quite a big difference. If you just think about it, 90% is 9 on 10, but 99 would be then, instead of 9 on 10, it would be 99 on 100. So although in terms of percentage points, it's not a lot, it can get a lot harder to calibrate your models at such an interval. So reading, a 95% confidence interval is defined as, we're definitely not going to use this word, right? As an interval of values such that with 95% probability, the interval will contain the true unknown value of the parameter. The interval is defined in terms of lower and upper limits computed from the sample of data. for linear regression, the 95% confidence interval for beta 1, this is what we're trying to estimate, approximately takes the form with this plus or minus. This is what you've calculated using least squares. There's just a formula for it, which we derive using calculus. It would be great at one point, even if we're a bit rusty at our if it's been a while since we differentiated anything, it might be a good idea. Obviously, it comes at a price. It means doing less new material, but you calculate your beta 1 hat using this formula. We're dividing two sums, and the first sum depends on your input data and your observed output data. Second sum solely on the input data. So once you've calculated that formula and you have an estimate of beta 1, so that's beta 1 hat, then you also need to calculate what does the S stand for? Is it standard? The standard error. Now, how do you calculate the standard error? The standard error is this formula over here. What does sigma represent? Sigma represents the volatility, the variability within the error term. So depending on your error term, interesting, but how would you calculate sigma squared? Would you know the error term? It's a bit of a question over there. We'll see how the book does it. I think I missed this yesterday. Although sigma is the variance, I think yesterday I was kind of thinking that sigma is the variance within maybe the y's or the x's. Instead, we're saying sigma squared is the variance of epsilon. I'll quickly remind you, the higher the variance of the error term, the longer, the further away you would expect the data points from the red line. So the red line is the true relationship, but it doesn't take into account that we are omitting useful information, other predictor variables that may add more certainty to our prediction if we had to allow for them. Epsilon is what's driving these differences between the red line and the actual observation. These differences come about because we are not capturing 100% of reality. Instead, we are using a model. A model, by definition, is a simplification of reality. I really think that's probably the easiest way of conceptualizing the error term, right? Epsilon is a mean zero random error term. You have that in every model because the model is a simplification of reality. If whatever you're trying to predict, we said the heights of individuals. I mean, there's just, you can go down to the molecular, to the DNA genetic level, and instead we try coming up with, the word is proxies, where we're saying, okay, I don't have the DNA information, and even so it wouldn't necessarily be so simple. I don't have the DNA of the individual. But if I know these things, it's kind of like, well, the word is a proxy. So how to explain that? Although I know you've definitely come across it before, as kind of like a surrogate. I don't have the DNA information, but I can get a good idea of what it would look like or what it should look like by looking at parents' heights, diet, the level of pollution, any sicknesses, any vaccines taken. That's why we have the error term. That's why we have the error term. And we're saying that to calculate the standard error, in our estimate of the slope, we need to divide the variance, so the variability, of epsilon. Interesting. But how would we do that? Strictly speaking, when sigma squared is estimated from the data, okay. So this is what in our first reading last session wasn't entirely clear. You'd calculate sigma squared by performing another estimate. So in general, you don't know sigma squared because you don't know the error term. But you can estimate it. By taking the residual sum of squares. You know that. That's just the difference between your model's prediction. Well, it depends. It depends on it is a function of your model, the difference between your model's prediction and the actual observation. And then apparently you divide it by your number of observations minus 2, and then you square root. So this is how we're going to calculate. Sigma squared. And sigma squared is then divided by this sum to create the standard error of beta 1 squared, which, or this was a very long way of saying, there are these 4 or 5 steps that we need to perform, computational steps, to come up with. Let's not lose sight of the big picture, and I'll do my best not to go into too much detail, or at least to keep on reminding you of what we'd like to achieve. What we'd like to achieve is this interval. It is centered at the least squares estimate of the slope. And then you're going to move to the left and to the right to create this interval. By how many units? Twice the standard error of beta 1 on either side. So the interval is centered at beta 1 hat, and you kind of have this symmetry. You move the same number of units to the left and to the right. Similarly for beta 0 hat. Okay, so standard errors can also be used to perform hypothesis tests on the coefficients. So hypothesis tests on the coefficients. What are the coefficients? Well, in this model, beta 0 and beta 1. The most common hypothesis test involves testing the null hypothesis. So what's the null hypothesis? You want to be conservative. You don't want to get overly excited that you've actually found a relationship. So you will always start by assuming H0, the null hypothesis, and that is there is no relationship between X and Y, your predictor variable and the output variable. Now, we pitched this hypothesis against the alternative hypothesis. There is some relationship between X and Y. So this is very, very early on, typically in the process of modeling. Do I have a variable that would appear to influence what I'm trying to predict? And we're going to decide yes or no. Do we accept H naught? If you accept H naught, it means that variable is, you can't just dispose of it. Or do we reject? Actually, you never reject. You say there's not enough evidence to reject. There is not enough evidence to reject the hypothesis. So mathematically, we're going to take this phrase in simple English, there's no relationship, and we're going to write it mathematically. Mathematically, this corresponds to testing whether, well, that the slope is 0 against that the slope is not 0. Since if beta 1 is equal to 0, then the model would simply reduce to y equals beta naught plus epsilon. Notice the absence of x, so x is not associated with y. To test the null hypothesis, we need to determine whether beta 1 hat, our estimate for beta 1, is sufficiently far from 0 that we can be confident, okay? So that takes us back to the confidence interval. Let's say that you've estimated, let's take the real line. Let's take the real line. And you've estimated beta 1. So let's call this beta 1. How have you estimated it? There is the formulae on that page where we minimize the RSS. Okay, so that's your beta 1. That's your beta 1. And it's, for example, negative, which suggests that there is a relationship. It is negative, okay? It's to the left of 0. Let's write it as 0. Okay, so it's 0. Okay, so if we had to blindly trust, now that's with a hat, right? Beta 1 with a hat, it's just our estimate. It's just our estimate. Now, if we had to blindly trust that estimate, if we just went ahead and said, okay, beta 1 hat is the true beta 1, then you would conclude, yes, there is a relationship. Beta 1 is not 0. So there seems to be a negative relationship. As I increase x, y decreases. But that's not the full story. That's not the full story. You also need to you also need to include the confidence interval. And that confidence interval might be like this, which means even if we are, this is the extreme, right? In an extreme scenario, if the true beta 1 is actually here, it's still negative. It's still negative. On the other hand, you could end up with a situation where this is your confidence interval. Now it includes 0. Now it includes 0. So there is less evidence. There is less evidence in favor of no relationship. Beg your pardon. There is less evidence in favor of an actual relationship between x and y, because now 0 is in here. 0, the true beta 1 may in fact be 0. It is within this confidence interval. Now, the question is, how far is far enough? This, of course, depends on the accurate. So how far is far enough? Is the true beta one sufficiently far from zero? Well, actually, I think I should say, is the estimated beta one sufficiently far from zero to conclude that beta one is not zero? How far is far enough? This, of course, depends on the accuracy of beta one hat. That is, it depends on standard error beta one hat. If standard error beta one hat is small, then even relatively small values of beta one hat may provide strong evidence that beta one is not zero, and hence that there is a relationship between x and y. Okay, there's quite a lot going on over there. And when I read this the first time yesterday, I can't say that I understood it fully. But all we're saying is that even if your estimate, even if your estimate of beta 1 is relatively small, so even if it's quite close to zero, of course, what on earth do we mean by quite close to zero? But even if it's quite close to zero, even if it's over here, if the standard error of beta 1 is also very small, then maybe the confidence interval will be something like this. And zero still isn't included. So if it's a 95% confidence interval, we could say we are 95% confident that there is a relationship between x and y, that the slope is not zero. In contrast, if the standard error of beta 1 is large, then beta 1 hat must also be large in absolute value in order for us to reject the null hypothesis. In practice, we compute what is called a t statistic given by this thing over here. So what are we doing? We're doing beta 1, our estimate of beta 1 minus 0. So you're calculating the difference. How far is our estimate from what the null hypothesis is considering? The null hypothesis is considering a zero gradient. And then you're dividing by the standard error. You're kind of making it relative. You're saying, oh, okay, but this means nothing. I mean, okay, what if it's 1 million away? What if it's 2 million away? We don't know. I mean, is 2 million a large number, a small number? That question doesn't really make sense. But if you divide by the standard error, now you're getting an idea. How does it compare to the standard error of beta 1? So which measures the number of standard deviations that beta 1 is away from zero. If there really is no relationship between x and y, then we expect that 3.14 will have, now this is going into statistics which we haven't introduced yet. We'll just read it. A t distribution with n-2 degrees of freedom. The t distribution has a bell shape, and for values of n greater than approximately 30, it is quite similar to the normal distribution. Consequently, it is a simple matter to compute the probability of observing any value equal to the absolute value of t, or larger, assuming beta 1 is 0. This is the p-value. Let's see how much we can salvage from this paragraph. Roughly speaking, we interpret the p-value as follows. A small p-value indicates that it is unlikely to observe such a substantial association. between the predictor and the response due to chance in the absence of any real association. I think we're going to skip this. We reject the null hypothesis. So what's the opposite of the null hypothesis? That there is a relationship between x and y if the p-value is small enough. Typical p-value cutoffs for rejecting the null hypothesis are 5 or 1%. Right. It's a pity. It's a pity that this section, unfortunately, because we made very good progress yesterday, but unfortunately, if you've never heard of p-value, this might not be the ideal session to explain it. Can we maybe see from this example to get a better idea? We're estimating. So we have intercept and TV. Okay, so this was which, had we typed it out somewhere? Yeah, it's this, right? We had to estimate. So it was, can we regress sales onto the TV budget? We need to estimate beta naught and beta 1, the intercept coefficient and the TV coefficient. And this is what we've done over here. This is your first step. Your first step is to estimate these two. And that's just those two formulae when we mentioned differentiation. You go a step further and you calculate the standard error, both for beta naught and for beta 1. You then calculate the t statistic. And how difficult is that? It's just this divided by this. So if I took out my calculator, do we get the 15? Yes, it would look like it, right? By dividing the pink by the orange. Yes, I have a calculator on me. And the next step is to divide 7.0325 by 0.4578. In fact, I have 15.36. Now, what do you do with the 15.36? This is when you have to look it up in a what are those called? Not a probability table. In a anyway, just call it a table. So the question is, what is the probability of getting 15.36? In fact, that probability is very, very low. It's a lot less than 0.0001. The lower this is, if the p-value is small enough, the lower it is, then excuse me, then the stronger the evidence is to reject the null hypothesis. We can do this a second time at a later stage, but as a rule of thumb, a small p-value, you reject the null hypothesis. So over here, look, over here, you're going to say, this is so small, If you look at the estimate of beta 1, which is this one, that you conclude, yes, there is a relationship between what was the model? We were relating sales against TV budget. So look, table 3.1 provides details of the least squares model for the regression of number of units sold on TV advertising budget for the advertising data. Notice that the coefficients for beta naught hat and beta 1 hat are very large relative to their standard errors. So is the standard error small or large? Well, on its own, you can't ask that question. There's no answer to that question. But compared, as a percentage to 7, it's not that large, right? It's not that large. So the probabilities of seeing such values of if H naught is true are virtually 0. Hence, we conclude that beta naught is not 0 and beta 1 is not 0. And there is a footnote. In table 3.1, a small p-value for the intercept indicates that we can reject the null hypothesis that beta naught is equal to 0, and the small p-value for TV indicates that we can reject the null hypothesis that beta 1 is equal to 0. Now, we've really been focusing on the second one, right? Is beta 1 equals to 0? Reading on, rejecting the latter null hypothesis allows us to conclude that there is a relationship between TV and sales. Rejecting the former allows us to conclude that in the absence of TV expenditure, sales are non-zero. So what we're saying is we have enough data to conclude that if we didn't spend anything on TV marketing, the sales would still be greater than 0 because beta naught is the y-intercept. It gives you the output when the input is 0, and in this case, an input of 0 means 0 advertising budget. Okay. Now, assessing the accuracy of the model. Once we have rejected the null hypothesis in favor of the alternative hypothesis, it is natural to want to quantify the extent to which the model fits the data. The quality of a linear regression fit is typically assessed using 2 related quantities: the residual standard error, which is what we've been discussing, right? And the R² statistic. Let's have a look. So table 3.2 displays the residual square error, the R² statistic, and the F statistic for the linear regression of number of units sold against TV advertising budget. So we have these 3 values. Okay, let's see. So let's start with the residual standard error. The residual standard error is this, isn't it? It takes your residual sum of squares, divides by basically your number of observations, but -2, and square roots. Okay, let's see. Recall from the model 3.5 that associated with each observation is an error term epsilon. Okay, the error term makes up for the model's limitations. Due to the presence of these error terms, even if we knew the true regression line, i.e., even if you knew beta naught and beta 1, we would not be able to perfectly predict y from x. The Residual standard error is an estimate of the standard deviation of epsilon, right? What do we mean by standard deviation? Standard deviation is the square root of variance. And variance is, just think of how volatile the data is, how spread out it is, how different two data points are from each other. The larger your variance, then there is more volatility within your data. If you square root the variance, you get the standard deviation. Roughly speaking, it is the average amount that the response will deviate from the true regression line. And it is computed using this formula. So this is what we read in the previous page. And what we're doing in the green is simply writing the definition of RSS. Which is that over there. Note that RSS was defined in section 3.1.1 and is given by what I've highlighted in blue. In the case of the advertising data, we see from the linear regression output in table 3.2 that the RSE is 3.26. So, in other words, actual sales in each market on average deviate from the true regression line by approximately 3260 units. Okay, so another way to think about this is that even if the model were correct and the true values of the unknown coefficients beta naught and beta 1 were known exactly, any prediction of sales on the basis of TV advertising would still be off by about 3260 units on average. Of course, whether or not 3260 units is an acceptable prediction error depends on the problem context. In the advertising data, the mean value of sales over all markets is approximately 14,000 units, and so the percentage error is 23%. The RSE is considered a measure of the lack of fit of the model to the data. If the predictions obtained using the model are very close to the true outcome values, that is if y hat I is roughly yi for each observation I, then 3.15, which is this, will be small, and we can conclude that the model fits data very well. On the other hand, if y hat I is very far from yi, for one or more observations, then the RSE may be quite large, indicating that the model doesn't fit the data well. Okay, I mean, there is quite a bit to digest over here. And I certainly, if you had to ask me to write this out without looking at the book, I would definitely struggle. But let's keep in mind what we're trying to do over here. We're assessing the accuracy of the model. Now, what do we mean by that? What do we mean by that? You know that there is a relationship. You know that there is a relationship if you've rejected the null hypothesis. Now we want to measure how well does the model reflect the data. And RSE is one one such measurement. The RSE is telling you that on average, the model's prediction actually, maybe I haven't understood this correctly. In other words, actual sales in each market deviate from the true regression line. The true regression line. Interesting. But we wouldn't know the true regression line, would we? So I'm actually surprised to see this written. I'm sure it's correct, but the model fits the data very well. But nowhere are we mentioning the true regression in the last paragraph. In other words, actual sales in each market deviate from the true regression line. Not entirely sure what we're getting at over here. We may have to go over it a second time. I mean, I guess the takeaway is the smaller this is, the better. But then the actual interpretation of a specific RSE, I don't feel I've quite understood it myself. I get this. The RSE is considered a measure of the lack of fit. If the predictions obtained using the model are very close to the true outcome values, the model fits the data very well. Yeah, I get all that. I get all that. It's this that has me slightly concerned. From the true regression line. Unless the true regression line means, what does true regression line mean? Does it just mean the line that we have? No, because they wouldn't be saying true, would? No, clearly it's the red, right? Yeah, the red line represents, but you normally wouldn't have the red line. I mean, we're just gonna have to cut our losses and keep pushing forward. You usually with these things, you look at it the next day, and somehow things are clearer. The RSC provides an absolute measure of lack of fit of the model to the data, but since it is measured in the units of Y, it is not always clear what constitutes a good RSE. The R² statistic provides an alternative measure of fit. It takes the form of a proportion. The proportion of variance explained, and so it always takes on a value between 0 and 1 and is independent of the scale of Y. So to calculate R², we have this formula, where TSS is the difference between each observation's output and the mean of the full set of outputs squared. It is the total sum of squares. And RSS is defined in 3.16. That's just the residual sum of squares. TSS measures the total variance in the response Y and can be thought of as the amount of variability inherent in the response before the regression is performed. Oh, I see. Okay. Actually, this is, I think, quite straightforward. This is actually quite straightforward. This gives you a measure of the variability within the output data. But before you do any regression, there are no hats over here. This is before you set up the model, before you do anything. You can always calculate that. That's just from your raw data. No model, no fitting. Now, the RSS is a function of what? Well, it takes your prediction, subtracts the actual, so that's y hat minus y, and it squares. Now what you want is, the lower the red is compared to the pink, you're kind of comparing variability against variability over here, which is why I guess you can divide them. We're not going to have units over here. Variability against variability. The lower the blue is, the closer R squared is to 1. So you want it as close as possible to 1. And we'll think about wrapping things up. We'll maybe read this page and we can call it a night. RSS, I'm reading over here. RSS measures the amount of variability. I really like this. The amount of variability that is left unexplained after performing the regression. Hence, TSS minus RSS measures the amount of variability in the response that is explained or removed by performing the regression, and R squared measures the proportion of variability in Y that can be explained using X. I think that's a really important sentence. R squared measures the proportion of variability of Y that can be explained using X. An R squared statistic that is close to 1 indicates that a large proportion of the variability in the response has been explained by the regression. A number near 0 indicates that the regression did not explain much of the variability in the response. Remember, variability will keep on appearing on a regular basis. There is no such thing as statistical learning if there wasn't variability. So you're trying to capture how Y varies as a function of X. So a number near 0 indicates that the regression did not explain much of the variability in the response. This might occur because the linear model is wrong, or the inherent error sigma squared is high. So if your error term has a very high sigma, even if you know the true relationship, that error term is, we're really going to keep an eye on the error term. The error term is everything that isn't explained by the variables that you're measuring, that you're allowing for in your attempt to predict the output. In your attempt to predict the output. So R squared, if it's a low R squared, then that's usually driven by two issues. Either the linear model is wrong, you shouldn't be using a linear model to try explaining the why, or else the inherent error sigma squared is, and you can't change that, right? That's just, you know, you choose to study a specific quantitative variable, and it just might be the case that there is a very large variance within the error term. So what you could do is you could try allowing for different, including more variables, or taking different variables. In table 3.2, the R squared was 0.61. And so just under 2/3 of the variability in sales is explained by a linear regression. I think this is really, really important. I think this is really important. 2/3 of the variability in sales is explained by a linear regression on TV. What we might try doing tomorrow is maybe taking a numerical example, but from because I think once we start 3.2, which is multiple linear regression, meaning you're expecting diagrams like this one now, where we have more than a single predictor variable. I would imagine it's the same ideas, but just in these higher dimensions. So it's the same kind of ideas, right? Look, TSS, RSS. But we may spend tomorrow's lesson, and maybe we'll take a numerical example as well. It's probably not a good idea at this stage to keep on pushing forward. This is where we need to consolidate our position. But we'll get there. We'll get there. What we need is, I think what we need is, we'll remember, I think it was 2 sessions ago when we were working in Excel, and we did something similar. I think it was when we were discussing the residual sum of squares. And we'll try doing something similar. We can't replicate this data because, unfortunately, if there is an advertising data set, I haven't been able to locate it, but we can create our own data, meaning it will be synthetic data. We'll assume that we know the true relationship to generate the training set. But this R squared, I don't think that this R squared is such a difficult concept. What the R squared is doing is it's giving, we are quantifying how accurate the model is. Now remember, the model will be the dark blue. The red is what we'll do tomorrow. We had already done this once in Excel. And we had actually even estimated beta naught and beta 1, and we had seen that those values coincided with what we had in R. But this idea of R squared, we're trying to get a handle on the error term. And I know I've done this quite a few times now, but please, it's really crucial. The error term is what is causing these observations to not be located exactly on the line. And the RSS is telling is not the RSS, the R squared is giving you an idea of how good your blue model is to actually how good the blue model is to actually describing the data. Okay, we'll end it over here. It wasn't an easy one. It will be easier tomorrow though. Thanks.